Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. The starting material is a dilithium dienolate derived from ethyl acetoacetate, ethyl 3-oxobutanoate. Treatment of ethyl acetoacetate with two equivalents of a strong base, like LDA or NBULI, generates a dianion, dilithioenolate. The structure shown is the dilithiodianion of ethyl acetoacetate. The two oli groups are on C1, the terminal methylene, giving CH2 is equal to C, oli, dash, and on C3, the alpha carbon to the ester, giving is equal to C, oli, dash OH. This is the dianion of ethyl acetoacetate where both the methyl ketone terminus, as a vinylogous enolate, and the ester alpha position are deprotonated. Moving on to the next step. Reactivity of the dianion with alkyl halide. In the dianion of ethyl acetoacetate, the more reactive, harder, more carbanion-like, nucleophilic site is the terminal carbon, the gamma carbon, C1, which bears the ioxomethylene. The less reactive site is the alpha carbon between the two carbonyls. Under kinetic conditions with a primary alkyl halide, CH3CH2I, alkylation occurs preferentially at the terminal, gamma, position, the more reactive carbanion. Moving on to the next step. The ethyl iodide alkylates the terminal carbon, the gamma carbon of the dianion, i.e., the carbon bearing the IChO is equal to CH2. This converts CH2 is equal to C, oli, to CH3CH2CH2C, oli, is equal to, after alkylation at the terminal carbon of the vinylogous enolate, the terminal CH2 picks up an ethyl group. And for the final step, protonation of both oli groups regenerates the carbonyl functions. The terminal oli becomes a ketone C is equal to O, and the internal oli on the vinyl position becomes the ester C is equal to O, restored. This gives CH3CH2CH2C is equal to O, CH2C is equal to O, OH, which is ethyl 3-oxohexanoate, ethyl 3-oxopentanoate with propyl group, consistent with option A. Option B would require alkylation at the oxygen rather than carbon, giving an O-alkylated product, vinyl ether, which is not the major product with a primary alkyl iodide under these conditions. Option C would require alkylation at the internal alpha carbon between the two carbonyls, which is the less reactive site in the dianion. Gamma alkylation is preferred. Option D would require double O alkylation or alkylation at the ester oxygen, which is not favorable. The major product is the gamma-alkylated compound after hydrolysis, CH3CH2CH2C is equal to O, CH2C is equal to O, OH, matching option A. Therefore, the correct answer is A. Therefore, the correct answer is option A.